Have you ever worked in a group on a project and someone had a great idea and then another one built off of that idea and then another person even built off of the ideas that were already presented, and pretty much after that you had this bulk of ideas that you could carry on and then complete the project? Well, that's kind of similar to what I think probably occurred once the trig identities for the sum or difference of two angles had been developed. Because remember, once we had the identity for the sum of two angles, we were able to say, well, if we know what the identity for the sine of the sum of two angles, or the cosine of the sum of two angles, or the tangent of the sum of two angles is, we could just make both angles the same and then develop and simplify what would be the double angle identities. And so over here I've written what we got for the double angle identities that we did in an earlier video. And links to the videos of the 8 fundamental trig identities, the identities of the sum and difference of two angles and cofunctions, and the identities for the double angle identities are in the description of this video if you haven't seen those and would like a review of them. Well, with these, once we had the sine of 2 alpha, the cosine of 2 alpha, and the tangent of 2 alpha, and we also had the 8 fundamental trig identities, we were able to say, well, the sine of 2 alpha, that's pretty much the only simplification we'll get for that identity. And the tangent of 2 alpha, that's pretty much the one that's used frequently for that one. But our original cosine of 2 alpha was that it was cosine squared alpha minus sine squared alpha. And then looking at it, someone said, well, wait a minute, there's square on the cosine or there's square on the sine. And recalling back to the 8 fundamental trig identities, there were the Pythagorean identities, and one of them specifically was that cosine squared an angle plus sine squared the angle is going to give me 1. Now remember, it's cosine squared plus sine squared the angle gives you 1. And this is cosine squared the angle minus sine squared the angle. That gives you the cosine of twice the angle. Well, back to the thing with the looking at the 8 fundamental trig identities along with this, with that Pythagorean identity, they made replacements for the sine squared alpha and simplified it to this form of the cosine of 2 alpha. Coming back up to here, they made a replacement for the cosine squared alpha and simplified it to this identity. And now with these two, another person looked at this and said, but in these identities on the cosine and then cosine to the first power of just twice that angle. And if we ever have it where there's the square on the trig function, but we really need it to get down to a first power instead of having a square on it, one of the ways we could do that would be to just rearrange this form of the double angle identity and see what we would have for the replacement. So if we take this cosine of 2 alpha is equal to my 2 cosine squared alpha minus 1 and solve for cosine squared alpha. Well, to do that, the first thing we would do would be to add 1 to both sides. So we have cosine 2 alpha plus 1 is equal to 2 cosine squared alpha. And then divide both sides by 2. And I'm going to write the cosine squared alpha on the left and the expression that it's equal to on the right. I have cosine squared alpha could actually be replaced by the expression cosine 2 alpha plus 1 all over 2. And actually, that all over 2, the division by 2, could be written as 1/2 times the expression. So another way to write it would be cosine squared alpha is equal to 1/2 times the cosine of 2 alpha plus 1. So what this does, if I take out the cosine squared alpha and replace it with that, it takes me down from a power of 2 on my trig function to a power of 1 on my trig function acting on the double angle with the rest of the expression. So this is considered a power reducing identity because it lowers the power from the second degree down to the first degree. And we can actually utilize it with higher powers, like if it's to the 4th power or to the 6th power, and make a replacement. Similarly, if I look at the cosine 2 alpha is equal to 1 minus 2 sine squared alpha, and rearrange and solve that one, we'll start with my cosine of 2 alpha is equal to the 1 minus 2 sine squared alpha. This one I'm going to add the 2 sine squared alpha to both sides and then subtract the cosine of 2 alpha from both sides, so I get a positive coefficient. And squared alpha, subtract the cosine 2 alpha, so this is 1 minus cosine of 2 alpha. And then divide both sides by 2, I get sine squared alpha is equal to, I can write it as 1 minus the cosine of 2 alpha, all divided by 2, or sine squared alpha, I can replace it with 1/2 times the quantity 1 minus cosine 2 alpha. And then again, it lets me take and reduce the power on the sine function from a squared power down to a 1st degree power. But look, these both came from differing forms of the cosine of 2 alpha. So even when I do the power reducing for the sine squared alpha, it goes back to an expression that has the cosine of twice an angle in it. The biggest difference between these, and remember addition's commutative, so you can change the order of the terms, and that means that sometimes you might see this as 1/2 times the quantity 1 plus cosine of 2 alpha for cosine squared alpha. But the only difference between these two power reducing replacements is that in the replacement for cosine squared alpha, it's 1/2 and then times the quantity with a plus between the cosine of 2 alpha and the 1. And in the sine squared alpha's replacement, it still has that 1/2, it still has the 1, it still has the cosine 2 alpha, but it's minus the cosine 2 alpha instead of plus the cosine 2 alpha. And then what about the tangent of 2 alpha? Well, I don't want to mess with having to go through and rearranging this whole thing for the power reducing because I also know that my tangent of an angle is equal to the sine of the angle divided by the cosine of the angle. So when I'm looking at making a replacement for tangent squared alpha, I can think of it as sine squared alpha's replacement divided by cosine squared alpha's replacement, and they have a common factor of 1/2 that'll cancel, and so this is just going to be replaced by 1 minus cosine of 2 alpha divided by, and I'll rewrite this the other way, 1 plus cosine of 2 alpha. So that's the development of the power reducing formulas. What I'm going to do next is I'm going to take a moment to rewrite these over to the side, and then we're going to develop the half angle identities, and then after that do several examples of either using the power reducing identities as well as using the half angle identities. Next, we're going to look at the half angle identities. And what happened with the half angle identities is that once we had these power reducing identities, looking at them, someone noticed that, well, if this is an alpha and that's a 2 alpha, then this on is exactly half of the angle that is being acted on in the parentheses. So if we actually looked at, instead of writing this alpha and writing at 2 alpha? What if we looked at just calling our angle inside the parentheses our original angle? Let's just call that theta, for example. So if I had 1/2 of 1 plus the cosine of theta, then holding the relationship true, I would still have a cosine squared, but the angle out here has to be half of the angle that's in there to meet the same requirement of the relationship between these. So this angle has to be whatever that angle is cut in half. So I have theta over 2 as the angle that it's acting on. And if you actually want to have a identity specifically for the cosine of half the angle instead of the square of the cosine of half the angle, we just need to take the square root of both sides. Remembering when you take the square root of both sides, you have to remember the plus or minus. And that gives me that the cosine of theta over 2 is equal to plus or minus the square root of 1/2 times 1 plus cosine theta. Or, like we saw earlier in the video, inside this radical you could write it with the 1 plus the cosine theta in the numerator, all with a long fraction bar, and the 2 in the denominator. Just make sure that whole thing stays underneath the radical. Now this plus or minus thing, we have to keep it along with us until we get to actual questions where we know the span of values that the angle theta is in. Because if we know the span of values that the angle theta is in, then we'll just take and divide each of those pieces of it, divide the beginning of the interval, divide the theta, and divide the end of the interval all by 2, and that will give me the span of values that theta over 2 would have to fall in. Once I know the span of values that theta over 2 has to fall in, I can identify what quadrant theta over 2 would be, and then I could determine whether I need to put the plus on this answer that I get, if my cosine of that theta over 2 angle should be positive in the quadrant that theta over 2 lands in, or the minus if the quadrant that the theta over 2 lives in is one in which the cosine of that angle would be a negative ratio. So this plus or minus we leave on there until we get to the questions and we know the span, and then where the sign is correct or is chosen for the cosine of theta over 2. So whatever that theta over 2 is in. Alright, now that gives me what's called a half angle identity, because it gives me the way of finding half of an angle or having a replacement for it. That gave me the half angle identity for cosine. Doing the same process on this next one will give me the half angle identity for sine. And notice again, both of these came from rearranging the cosine of twice an angle cases. And so when I do this, I'm still going to have the cosine in that right hand side. So the sine of theta over 2 is equal to plus or minus the square root of 1/2 times 1 minus cosine of theta. And then when we look at the whole process with the tangent of theta over 2, that's going to be plus or minus the square root of the 1 minus the cosine of theta divided by 1 plus the cosine of theta. So for each of these, we have our half angle identities. Now, as also was stated before, these are 3 of the 6 trig functions. We also have the secant of theta over 2, which would be the reciprocal of this right-hand side. The cosecant of theta over 2 would be the reciprocal of that side. Cotangent of theta over 2 would be the reciprocal of that side. Okay, with all of these identities now developed and ready to go, let's look at some examples. Now for the examples. The examples that I'm going to do, the first one is going to be an example of a power-reducing identity type question, and then the second one is going to be with the half-angle identities. So let's look at the first one. It says write sine to the 4th theta in terms of the first power of one or more cosine functions. Now, it didn't actually need to tell me that they were cosine functions because our power-reducing formulas came from a rearrangement of the cosine of twice an angle. It was just kind of an extra hint in the question. It could have just told me to reduce the power of this trigonometric expression, and then I would have had to have gone to these power-reducing identities and applied it from there. Let's go on and see what we're supposed to do. Well, this is sine 4th theta, and remember that means sine theta quantity to the power 4. Now I don't specifically have one where I replace for the sine quantity to the power 4, but that exponent of 4 is an even exponent, and I can actually write this power 4 as work on my sine squared theta to the 2nd power. So remember, sine theta to the power 4, I could write as sine theta squared and then that quantity squared, because if you take an exponential expression that has a base to exponent yet another exponent, you keep the base and multiply the exponents. So it would mean the same thing as 4th power if I have 2nd power, because that would be 2 times 2 or power 4. So it means the same thing. But what it does for me is it gets it to the point where I have my first replacement. So sine squared theta can be replaced by, and also when you're doing these problems, make sure that you use the angle that you're supposed to from the question that you're working. The pattern of what you are supposed to do is over here, but you want to make sure that you use the angle that is appropriate for your question. All right, so my sine squared theta, I'm going to take that sine squared theta out and replace it with 1/2 times 1 minus cosine 2 theta. So I just replaced it in there. Now, 1/2 is multiplied to it, and when you take a multiplication and you raise it to a power, each of the factors get raised to that power. So 1/2 times 1/2 is 1/4. So squaring 1/2, I get 1/4. And then squaring out 1 minus cosine 2 theta, well, remember that's 1 minus cosine 2 theta times another 1 minus cosine 2 theta. So you need first, 1 times 1 is 1. Outers, 1 times negative cosine 2 theta is a negative cosine 2 theta. Inners, negative cosine 2 theta times 1 is another negative cosine 2 theta. So negative cosine 2 theta minus another negative cosine 2 theta is minus 2 cosine 2 theta. And then last, negative times negative is positive, and cosine 2 theta times cosine 2 theta is cosine 2 theta squared, but to write that we tuck it in between the trig function name and the angle. So we have our plus cosine squared 2 theta. Now that's what goes here. Now, I'm not quite done because I still have a square on this cosine of 2 theta, and it wants me to go to the first power of all my trig expressions. So I still need a replacement for that. But this time the square is on the cosine of an angle. So to make this replacement, I have to go to where I have the power reducing replacement for cosine squared an angle. But remember, this 2 theta is now my working angle. So a replacement for cosine squared of, think of the alpha being your 2 theta, is going to be 1/2 times the quantity 1 plus cosine of twice whatever that angle is. So twice 2 theta is 4 theta. Okay, so I'm going to bring this line up over here to finish off and to simplify our final expression. So from inside the parentheses, I've got a nested set of parentheses, so let's distribute that first. So that will be 1/4 times my 1 minus 2 cosine 2 theta, then plus 1/2, and then plus 1/2 cosine 4 theta. So all I did here is I have my 1/4 open parentheses 1 minus 2 cosine 2 theta plus 1/2 plus 1/2 cosine 4 theta. Now let's go ahead and distribute the 1/4. So 1/4 times 1 is 1/4, and 1/4 times a negative 2 cosine 2 theta is a negative 1/2 cosine 2 theta. 1/4 times 1/2 is plus 1/8, and then 1/4 times 1/2 cosine 4 theta is plus 1/8 cosine 4 theta. And then lastly, 1/4 plus 1/8 is 3/8. So I have 3/8 minus 1/2 cosine 2 theta plus 1/8 cosine 4 theta. Sorry about the lack of organization there. These get a little bit longer than I anticipated it to go. But that is my replacement for my sine of the 4 theta. And you're like, why would anybody ever do that? Why would you take this longer expression and put it in for something that's so concise as that? Well, there are operations in calculus where the process can't be done or isn't an easy thing to do if it's got that power on the trig function and I don't have other components in that problem. But it's much easier to do if I have a first power on it. So this power reducing identity work, it really comes into play when you take your first calculus course and you get into what's called integration. So while it looks so much messier here than it did in its original form, there are places in mathematics where it is beneficial for us to be able to do that. Let's look at this last one, which is find the exact value of the sine, cosine, and tangent of theta over 2. So the half angles given this information. So now we're going to be looking at those half angle identities. And there's a couple things we want to do. We want to look at cotangent of theta is 5/12, and theta is in the span from 180 degrees to 270 degrees. Or that might have said from pi to 3 pi over 2. Looking at that being the span of theta, that means theta is in the third quadrant. So when I come over and I draw my diagram for my trig angle and standard position, and always go to the nearest x-axis with your reference angle. Remember, cotangent is x over y, or we could also say adjacent over opposite. So I have my -5 being my x-coordinate and -12 being my y-coordinate. So I needed to make sure I put those negatives in there if I'm looking at that value of it. And then the hypotenuse we would get from the Pythagorean theorem, and from the Pythagorean theorem you'll get that your hypotenuse is 13. It's a Pythagorean triple. Now also, my theta is between 180 and 270, but I've got to pick the right sign for where theta over 2 is. So I really want where theta over 2 is. But I can't just divide one part of the inequality by 2. I have to divide all 3 portions of the inequality by 2 to get an equivalent statement. So 180 degrees divided by 2 is 90 degrees, is less than theta over 2, which is less than 270 degrees divided by 2 is 135 degrees. And that span of 90 degrees to 135 degrees, that's in quadrant 2. So I'm going to pick the right sign for a quadrant 2 angle with these trig functions. So let's do the first one, which is the sine of theta over 2. And so the sine of theta over 2, that's that one. Theta over 2, think second quadrant. The sine of a second quadrant angle is positive. You have to go up. So we're going to pick the positive. The square root of 1/2 times, so I'm just looking at this formula right here, 1/2 times 1 minus the cosine of theta. So 1 minus the cosine of this angle theta. And the cosine of this angle is adjacent over hypotenuse. So my sine of theta over 2 is going to be the square root of 1/2 times 1 plus 5/13. Well, 13/13 plus 5/13 is going to give me 18/13. And 18/13 times 1/2 is going to give me 9/13 when you take the 2 into 18. And then square root of the 9/13, if we want to rationalize this, we'll build top and bottom by 13 in the radical. And get that this is, well, in the numerator, a 3 will come out, but the 13 has to stay in. So that's 3 times the square root of 13 all over, in the denominator I have 13. So my sine of theta over 2 is 3 times the square root of 13 over 13. Now let's do the cosine of theta over 2. The cosine of theta over 2, well, theta over 2 is a second quadrant angle. And the cosine in a second quadrant is negative. So it's equal to negative the square root of, and cosine of theta over 2, 1/2 times 1 plus the cosine of theta. So 1/2 times 1 plus, and my cosine of theta is negative 5/13. So now we have our cosine of theta over 2 is equal to negative the square root of, well, 13/13 plus a negative 5/13 is going to give me 8/13. And 1/2 of 8/13, 2 as a common factor will give me 4/13 underneath the radical. And then to rationalize, we'll multiply top and bottom of the fraction in the radical by 13, and a common factor of 2 will come out. So this will be negative 2 times the square root of 13 all over 13 for the cosine of theta over 2. So the sine of theta over 2 was 3 times the square root of 13 over 13. The cosine of theta over 2 is negative 2 times the square root of 13 over 13. And while I could go through and do this formula for the half angle for tangent, and it's actually a good idea to do it for practice and then see that you get the same answer, you can also get the tangent of theta over 2 by just taking the sine of theta over 2 and dividing it by the cosine of theta over 2, since we already have that. So for our question here, the tangent of theta over 2 will be equal to, and when you take the sine of theta over 2 and divide it by the cosine of theta over 2, you're going to flip it and multiply it. You're going to get our value of a negative 3/2. So the square root of 13s will cancel, the 13s will cancel. Positive divided by negative is negative, and it'll be 3 in the numerator and 2 in the denominator. So that gives you some examples of how to apply the power reducing identities, as well as how to work out the work with the half angle identities.